All right, let's talk about something at the very heart of AI. How does a machine, something that really only thinks in simple, straight lines, learn to understand the complex, curvy, messy world that we live in? Well, today we're going to find out by building a neural network right from the ground up. So here's the plan. We'll start with the challenge we're trying to solve. Then we'll build a really basic model, and honestly, watch it fail. After that, we'll give it a serious upgrade, pit the two models against each other in a showdown, and then we'll get into why this one little difference is really the key to understanding all of modern AI. Okay, first things first, the challenge. Before we can teach a computer to do anything, we've got to be super clear about what we're actually asking it to do. You know, at its core, this all starts with a technique called supervised learning. It's kind of like this. We give the computer a whole bunch of problems, but we also give it the correct answers. Its job is to figure out the pattern, the relationship between the two, so it can start predicting answers for new problems it's never seen before. The specific kind of task we're tackling today is called regression. Now, this isn't about picking a category, like, is this a picture of a cat or a dog? No. Regression is all about predicting a specific number on a sliding scale. A classic example is trying to predict the price of a house. Based on things like its size and location, you want to predict a very specific dollar amount. That's a regression problem. All right, time to get our hands dirty. Let's build our first attempt, the basic model. We're going to see what happens when we throw a pretty tricky, curvy problem at a very, very simple machine. So here's our mission. We need to predict an output, y, based on two inputs, x1 and x2. But here's the catch. The formula that connects them isn't a simple straight line. It's this weavy, complex relationship using cosines and sines. This is where things get really interesting. We follow a pretty standard recipe here. First, we cook up a data set with 5,000 examples. Then, we define our model's architecture, and in this case, it's about as simple as it gets, just a single neuron. And finally, we train it. We show it all the data 200 times, and each time it tries to tweak its own settings to get just a little bit better at predicting y. So, what happened? Well, you can see for yourself. The model, it tries. It really does. But it's just completely out of its depth. Because it can only think in straight lines, all its predictions form this flat plane. It's like trying to perfectly cover a wavy, lumpy blanket with a stiff, flat piece of cardboard. It's never going to work. Okay, so that was a failure, right? Our basic model just couldn't handle it. So how do we fix this? Well, it's time for an upgrade. It's time to give our model a kind of superpower that will finally let it see the world in curves. And this really gets to the absolute heart of the problem. The source material says it perfectly. The model's biggest limitation is that it's linear. It was built to solve straight-line problems, but we gave it a curvy one. It was the wrong tool for the job. I love this analogy because it just makes everything click. Our first model was like trying to draw a beautiful curve, but all you have is a hard, straight ruler. You just can't do it. What we need is a flexible ruler, one that can bend and twist and adapt to trace any shape we want. And here it is. This is our flexible ruler. The upgrade is actually pretty simple on the surface. We just add one hidden layer with 10 neurons. This layer uses something called an activation function, which you can think of as a little switch that allows the network to introduce bends and curves into its thinking. This is what gives it the flexibility to learn much, much more complex patterns. All right, enough talk. Theory is great, but let's see this thing in action. It is time for a showdown. We're going to build this new, more powerful model and put it head-to-head against our original, simple one. And to make it a totally fair fight, everything else is going to stay exactly the same. We use the same data, the same training process, everything. The only difference, the one variable we're testing, is that crucial little change in step 2, the addition of our hidden layer. And just look at the difference. I mean, wow, it is night and day, isn't it? The upgraded model's predictions no longer form a flat plane. It's this dynamic, curved, beautiful surface that almost perfectly mimics the actual wavy pattern in the data. This is what learning looks like. So let's get down to the brass tacks, the actual numbers. We measure how good a model is by its error score, and lower is always better. Our first, simple model came in with an error of 0.9234. Just keep that number in your head for a second. Now, what about our upgraded model? Well, check this out. It scored a test error of just 0.4960. That's a massive, massive improvement. When you see them side by side like this, it's no contest, right? The advanced model with the hidden layer didn't just win, it cut the error almost in half. This wasn't some tiny little tweak, this was an absolute game changer. Okay, so what's the big lesson here? Beyond just this one little experiment, why does this simple comparison matter so much in the grand scheme of AI? It all comes down to this, that one hidden layer isn't just a minor detail, it's the secret sauce. It's the core concept that transforms a simple calculator into a powerful learning machine. This ability to handle nonlinearity is what allows AI to understand human language, to recognize faces in a crowd, and to solve problems that we once thought were impossible for computers. So let's sum it all up. A few key takeaways. First, the real world is complicated and curvy, and our AI needs the right tools for that. Second, that hidden layer, it's the basic building block of pretty much all modern AI. But we also have to be careful. Things like randomness can affect the results, and just piling on more layers isn't always the answer. Sometimes that can lead to a problem called overfitting, where the model basically just memorizes the test answers instead of actually learning the subject. And that kind of brings us to our final thought for today. We just saw the incredible power that was unlocked by adding just one hidden layer. So it begs the question, right? What happens when you don't just add one, but you add hundreds or even thousands of them? Well, that is the question that defines the entire frontier of deep learning today.